Hello everyone and welcome to this presentation of our work about CoOP, a V2V-based cooperative overtaking maneuver for platoons on freeways. My name is Julian Hajnowski and this work is a collaboration with my two co-authors Martin Strunz and Falco Dressler from Technical University of Berlin. So let's have a quick look at platooning. Platooning describes multiple vehicles driving in convoys, often referred to as road trains. Vehicles in our case here are passenger cars. These vehicles then drive at a very short inter-vehicle distance, which is allowed by a specific cruise controller and vehicle-to-vehicle or in short V2V communication. Platooning promises several benefits, among others, that is a reduced fuel consumption and an increased safety and convenience for the passengers. But now let's consider the situation depicted here. We have a platoon approaching a truck in front of it, and this truck is driving slower than a platoon. Now the platoon is stuck behind this truck and cannot drive at its optimal speed. Therefore, the platoon benefits are reduced and, most importantly, the overall travel time will be increased. Therefore, we want to have overtaking also for platoons, because we don't want to lose our benefits. The issue here is that, to the best of our knowledge, no cooperative or not cooperative overtaking maneuver for platoons exists so far. There's only solutions for individual autonomous vehicles. Therefore, the goal for this work was to propose an overtaking maneuver for platoons on freeways that is able to let the platoon overtake the slow vehicle without splitting it into individual vehicles, because this would add additional overhead due to maneuvers. The overall maneuver, of course, should be executed in a safe manner. That means that other road users, in particular interfering vehicles, need to be considered, and we want to avoid collisions with them, of course. And lastly, this algorithm here, this maneuver, should only use local sensor data from the platoon members and exchange this data with intra-platoon V2V among all the platoon members. Besides these goals, we also had the following assumptions. So first of all, besides the specific cruise controller and the V2V communication that is required for platooning itself, our vehicles in a platoon have 4 sensors, that is 2 radar sensors in the front and the rear, and 2 side cameras that are able to detect objects in their vicinity, and for the radar sensors even measure relative distance and speed. In total now we get 6 sensor areas that are depicted in this picture here, which we are going to use to assess the maneuver area. Our intra-platoon V2V communication is not specific to any technology, but it can be unreliable. That is, messages can be delayed or even lost. And lastly, we do not have any further technical requirements to the other road users. So now let's have a look at the proposed CoOP concept. Here, the leader, that is the first vehicle in a platoon, is responsible for the overall overtaking maneuver. Therefore, the leader is in one of these 4 phases. In the beginning, he's in the phase 1, the decision phase, where he needs to decide whether to overtake a vehicle or not. Then he is in phase 2, the actual lane change phase, so lane change to the left into the overtaking lane. Then he is in phase 3, which is the passing phase. And then finally he is in phase 4, changing back to the original lane. In contrary, the follower here is not aware of the overtaking maneuver. The follower here is just responsible for reporting the sensor data when requested by the leader and to perform the lane changes again when requested by the leader. So now let's have a closer look at the leader's perspective. First, the leader is in the idle mode, and once the vehicle is detected by the front radar, the leader switches into phase 1, which is the decision phase. He then has to decide whether it is useful and possible to overtake this slow vehicle, which in this case just means that there is a speed gain for the platoon. This decision the leader only takes by considering his own sensor data and information about the platoon. When the decision has been made, he switches into phase 2, which is lane change to the left. Then he requests all the sensor data from all his platoon followers to assess whether the maneuver area is free. And if this is the case, he instructs all the followers to actually perform the lane change into the overtaking lane. Now the leader is in phase 3, which is the passing phase, where he has to decide when the slow vehicle is passed and when to change back into the initial lane on the right. Here the leader again only uses his local sensor data to monitor the front right area and the information about the platoon, and he decides to change back once it's not useful or possible anymore to overtake further vehicles. Then he changes to phase 4, lane change right, where he again requests all the sensor data by all the followers, and if the maneuver area is safe, he instructs all the followers to change back to the original lane, and then the maneuver is completed. Now that we've designed our algorithm theoretically, we of course wanted to address its behavior practically. For this, we chose a simulative approach. Our simulation environment consists of Sumo for simulating other road users, for example trucks, and Plexe for simulating the platooning functionality. We of course made sure that first of all our finite state machine implementation is correct by using unit tests and PyTest. And we made sure that our algorithm is safe and robust by simulating 24 different test scenarios. One of these test scenarios you can find here. You see that there is a platoon who wants to overtake the slower driving truck. It actually does so, but since there is a different vehicle, this vehicle also needs to be overtaken by the algorithm before changing back to the original lane. Now that we know that our algorithm works correctly, we of course wanted to address its performance. For this, we compare the following cases. First of all, we have the no overtaking case. So here the platoon is essentially stuck behind the slow vehicle, and this we consider to be the worst case. Next, we have the artificial long vehicle, or in short ALV case, which is just a single vehicle that has the exact same length as the platoon. We consider this to be the theoretic optimum because we have instant sensor data and the vehicle only needs one lane change per lane change maneuver. Finally, we have the oracle case, which represents an experimental lane change algorithm from Plexe. In this algorithm, the platoon leader has omniscient knowledge. That means it does not require V2V communication to obtain all the sensor data, but the lane changes of the platoon members are performed individually. We expect our algorithm to perform better than the no overtaking, of course, but worse than both of these theoretic optimal cases. So now let's have a look at the simulation results. In the simulation, we considered a freeway with 3 lanes and random traffic consisting of passenger cars and trucks with different speeds, and a single platoon consisting of 4 passenger cars that needed to drive for 20 kilometers with a desired driving speed of 30.6 meters per second. Since one of the main goals for overtaking is to optimize the travel time, we now look at the average driving speed of the platoon in medium traffic. First of all, we see that with no overtaking case, the average driving speed decreases massively in comparison to the desired driving speed. Whereas with the other 3 approaches, which actually perform an overtaking maneuver, the driving speed is close to the desired driving speed. ALV is, as expected, the best approach, but our CoOP algorithm is only 1% slower than the theoretic optimum here. In fact, it is even better than the oracle approach, which was a little bit surprising. The reason for that is that with CoOP, the decision to overtake the slow vehicle is performed as soon as possible and as soon as the vehicle is detected by the leader. Whereas in the oracle approach, it takes quite some time until the leader decides to actually overtake this vehicle. And in the meantime, the platoon needs to decelerate because it is stuck behind the slow vehicle. Now we also modified the traffic density. We added simulations for low and high traffic density, and we expect that with a higher traffic density, the probability to find a gap when we want to overtake is lower, whereas with low traffic density, the probability is higher. And in fact, we can see exactly that. For all algorithms with a higher traffic density, it is harder to find a gap when actually performing the overtaking. ALV is again, of course, the best approach. And now we actually see that CoOP is worse than the Oracle approach as well, because now we have exactly the effect that messages are unreliable or delayed, and it takes some time to obtain all the sensor data. And in the meantime, the gap that was open when we decided to overtake has been closed already, and therefore the average driving speed for CoOP is lower. This effect becomes even more prominent when we increase the length of the platoon. That is, when we increase the number of cars in the platoon. We performed simulations increasing the size of the platoon in the paper as well. So in conclusion, in this work, we propose CoOP, a V2V-based cooperative overtaking maneuver for platoons on freeways. CoOP allows overtaking for entire platoons without splitting the platoon into individual vehicles. It only uses local sensor data from the platoon members and exchanges it via interplatoon V2V. It is able to dynamically react to other road users and to avoid collisions with them. It is also robust against communication delays and even communication failure. And with all of that, it even increases the driving speed in comparison to no overtaking, of course, and it is even close to the theoretic optimum, that is the ALV and the Oracle case. In future research, we want to consider splitting the platoon in specific scenarios where it might be beneficial, and we, of course, want to add V2V communication with other road users to even further increase the cooperation between the vehicles. This concludes my presentation about CoOP. Thank you for your attention, and if you have questions, feel free to ask. Thanks.